All right, let's look at this called dimensional analysis. This is our last major concept for this unit. We'll talk about one more later in the week, but this is the last big one that we really got to get down before next week. All right, and so the idea is this is a means of problem solving, right? And so instead of memorizing and trying to remember a bunch of different equations, what this does is it gives us a means to think and come up with ratios that are going to help us solve the problem. And when we get to the end of the year, it helps us with just general math kind of at the beginning. But when we get to the end of the year, it'll actually help us do what we call stoichiometry, and that's a nice means of using this. So basically, it starts off with know what you're starting with, right? Also know or find useful ratios, right? And we'll talk about what that is in a second. So you start with what you know. You find ratios that are going to be useful, and we'll talk about what that means. And then what we do with those ratios is we manipulate them, right? With the goal being to cancel the previous unit. Okay, that's the important part. We're going to use ratios to cancel the step that came before. And that can look a lot of different ways, but basically if you understand multiplication and division, when we're talking about units, they work the same way, not just numbers. All right, and so we're going to finish with the desired unit. So whatever the problem asks us to solve for, we keep on going until we get that. Now you can kind of go round and round and round in some circles, but I'll show you how to try to think logically and go from there. So basically we got to know this. We have to know what ratios are. Ratios are, another name for them is fractions, right? Or equalities. And so what I want to show you is there's lots of different ways the same thing can be shown to you, right? So we have 12 milligrams divided by milliliters, right? 12 milligrams per milliliter is this one, right? And then we have, if that thing would get out of the way, we have 1 milliliter is equal to 12 milligrams, or vice versa, 12 milligrams equal 1 milliliter. Or we have 12 milligrams per milliliter in words, right? All of these mean the same thing. All of these are ratios or equalities. They're equal to each other. And so these are, when we think back to Sig Figs, this is like what we're talking about when we're talking about those perfect fractions, those perfect ratios, where the number of Sig Figs doesn't matter. Like if we looked at, the 1 milliliter, that's showing us 1 Sig Figs, but we could just as easily say 1.000000 milliliters is equal to 12.00000 milligrams if that's a known value that's given to us, if that's a known ratio, okay? Just like saying 1 dozen is equal to 12. Same thing. We can use those numbers if we look up their known quantities. And so what we got right now is we're going to do a couple problems together in order to solve this. So let me show you the first problem. It says that density of lead is known to be 11.3 grams per milliliter. What is the mass of lead that has this defined volume? All right, I'm going to bring up. So try to get myself out of the way a little bit. We're going to take a look at that problem. I know I'm on a different page, so maybe go back and take a look at it. But basically it says the density of lead is known to be 11.3 grams per milliliter. Noticing that's a ratio. And what is the mass of lead that has a volume of 45 centimeters cubed? So basically what we have is we have a known quantity. We have 45 centimeters cubed, right? We know that. 45 centimeters cubed is what we have. We also have 11.3 grams per milliliter. And it's asking us for, our question is, what is the mass? All right, so when we're looking at it, that's basically all we need to know. We need to know the mass. Well, the mass is going to come from that unit right there. It doesn't say specific. It doesn't say find it in pounds or find it in ounces or find it in kilograms. It just says find the mass. So in this case, if we can just get that left by itself, we're good to go. Okay. And so we know we're going to use that unit. Now, one of the things that we want to take a look at is this guy is also a ratio. Okay. So that's our first one. And the thing that we're left with, our known quantity, right, is this 45. And so to solve this problem, we're going to start, like it says, with what we know. We have 45 centimeters cubed. Great. So what we're looking for in our ratio is centimeters cubed. We don't have it, okay? And so one of those ratios that we looked at earlier, another ratio that we want to be able to use, right, is we saw, and this is inequality, we saw that 1 milliliter is equal to 1 centimeter cubed. We use this ratio in order to convert from a liquid unit to a solid unit, or vice versa. And so what we're now is we're going to do our first step. That in the problem, there are certain ratios or equalities that you're expected to know, and that's one of them. And so when we take a look at this, we're going to use that. And so we're going to do this. I'm going to show you it in another way, and it kind of just depends what you like. But we're going to use this ratio. And knowing that we want to get rid of the centimeters cubed, I'm going to put centimeters cubed on the bottom. Because mathematically what this does is it cancels them out, and that's the goal. A centimeter cubed times, or divided by, in this case, a centimeter cubed is equal to 1. We got rid of it. That's exactly what we wanted. And what that's equal to, that's where our ratio comes in. So this is equal to milliliters. And we get numbers, it's 1 and 1. So the only reason we did that problem, it doesn't help us numerically, right? This doesn't do anything for it. What it does is it shows, all right, I can convert from centimeters to millimeters, because if I press equals right now, I would have 45 milliliters, okay? That doesn't really help us right now. So my next step, all right, is to keep going. All right, and it says we need to manipulate ratios. We need to get rid of the unit that is not helping us out. Well, we don't want milliliters. We want grams. And so what I'm going to do is I'm going to put milliliters on the bottom and hope I have something that takes care of it. And I do. That's what it is right here. So I'm going to put my grams up top. Now this number, this is where some people get confused. That number is associated with grams. So I'm going to put the 11.3 right there. And what's going to go on the bottom? I don't see a number there. Well, it's a 1, right? 1 milliliter is going to equal to whatever's on top. If it's a 2, we'd have to double it. So I'm going to put a 1 right there. And now this one's nice and easy. The math isn't super hard because of just the system that we're using. But basically what we just did is we also canceled out that unit. And when we press the equals right now, we're left with the unit of grams. And that's what dimensional analysis does. Yes, we could have went and found the density equals mass over volume equation, and we could have put it in there. But even if we would have chucked those two numbers in there, unit-wise, it wouldn't have worked out. Okay, so at this point, we're going to put those two numbers in there. So I have 45 times 1 divided by 1 times 11.3 divided by 1. Now, again, do we really have to put in the ones? Nope. But just so you can kind of see how that would work out. And so our answer comes out to be 508.5. Okay? So the last thing we have to do is we have to check Sig Figs. Now, what I told you, ratios are perfect. So there's 3 and 1, 1 and 1, and there's 2. These, we don't care about their Sig Figs because these have infinite number of Sig Figs. We could put as many zeros after all those numbers and it would still count for the same thing. So really, when it comes to these problems, we're only looking at the number on front, the number that we found by calculation or we found by observation. All right, that's really the only one that matters because that's the only one that's not perfect. We measured it somehow, and that's what we did last week, right? So if that's got 2 Sig Figs, I got to look at this guy for 2 Sig Figs. So we're multiplying. So I'm just going to count back 1, 2. All right, that's an 8. So my final answer is going to be 510 grams. Should I put a decimal place right there? Right? There's no. Why? Because if I put a decimal place there, all of a sudden that one's position would count as a Sig Fig and I have 3. All right, so this is our answer. All right, so not only are we taking a look at Sig Figs, we're also taking a look at scientific notation if we need to, and we're taking a look at our new concept of. So let's take a look at the next problem. It's not even really a problem. Look at that thing. Okay, so we're going to use that. I would write all of those units down, hit the pause button, write them all down, and then we're going to talk about it in a second. All right, let's take a look at this question, right? So it says, how many inches could you travel if? How many inches could you travel if? And we have all those units you just wrote down. So we're looking at a car is 56 L per HR. We look at 1 foot equals 0.000189 miles. We look at another thing that has a car label and it's 105 kilometers per hour. We look at another unit that says 1 kilometer is equal to 0.6214 miles. And then we look at another one that says gas is 47 liters. So we have 5 different systems of numbers there. And what we need to work with is which one is the one to start with. Which one is not the ratio, if we can all do it? Which one is just a number? If you can find that one, you are probably off to a pretty good start. So in this case, it says that gas is 4 liters. So that's all I would write down. I would just write down 47 liters. Okay, you're gonna have to pay attention because you can't see it on my screen. What would come next, right? And this is what you got to get really used to. The next piece would be, all right, even if I don't know what I'm doing, I know at a minimum I need to do that. I need to get rid of liters, right? I'm starting with 47 liters. I need to get rid of liters, and so I need to cancel that. So look back at your units. Is there something that have liters in it? And there is, right? Liters is compared to hours. Now, it says it's 56 liters per hour. Again, we can manipulate that. So it says 56 liters. So I put the 5, 6 on the bottom, and it says per hour, so we're just going to assume that that's 1 because it's per 1 hour. It would have to tell us if it was something different. All right, so we have this one done. We're left with liters. We're trying to get to inches, and hours isn't getting us any closer. So next step. All right, I put that there. What am I trying to do? I'm trying to get rid of hours. I'm trying to get rid of the unit I was left with in the first place. So let's get rid of hours. And what can we compare it to? So look back at all of the ratio I gave you. And there's one without it. And it is being compared to kilometers. We're getting close to the right track, right? We had no idea how we could turn liters into, but we're getting there. All right. And so we put in our numbers. And so again, this one is 1 hour. And it says that we have 105 kilometers. So I cancel out my hours and I'm left with that. Okay, let's go to the next one. I have kilometers. I don't want kilometers, right? I got to get rid of it. So I know my next step is, all right, let's put kilometers on the bottom. What else do we have kilometers tied to? So let's look up there. Oh, there is something. There's something to do with miles. Okay, and what it's saying is 1 kilometer is equal to 0.6214 miles. And again, I did that because I wanted to cancel out my kilometers. All right, getting closer. All right, what do we have left? So on miles, that's good. I'm getting closer to our right system. What can I do next? I need miles on the bottom. Don't just put an M. At least put an MI because M would stand for meters and you'd be wrong. Do I have something? Yes. I have miles and I can compare that to feet. And it says 1 foot is equal to 0.000189. All right. Is that good? Sure. Some of you might have put 5,280 feet per 1 mile, but I decided to screw it up and go that route. And so that's pretty good. All right, so miles cancel. Now that's the last thing I gave you, right? But we need to get to inches. We don't want it in feet. So you should know this one, right? 1 foot is equal to 12 inches. And if we do that, we can now press equals because the unit that I want is the only one that is left. So let's put it into our calculator. Okay, so putting it into our calculator, we have 47 divided by 56. I'm not going to worry about the 1 times 105 times 0.6214 divided by 0.000189 times 12. Okay, I didn't put any of the ones in. Our answer comes out to be, oh boy, that's a long guy, 3, 4, 7, 6, 8, 8, 0.952. Great. What do? We got to take a look at significant figures. Now remember, all of these ratios are assumed to be perfect. Okay, are they? Probably not, right? That one is. Could this be? Yeah, they're made up. So in any case, we don't need to worry about any of these in these type of problems. We just got to worry about this guy on front. How many significant figures does it have? Okay, we have this arbitrary number of liters. It is 2, and so we're going to count on here. We're going to count back 1, 2, and we're going to round from there. And so that 7 pops it up. So we end up with 3, 5, and the rest becomes zeros. 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. And this is in inches, which makes sense. It's really, really big. But a better answer for that would be, in scientific notation, 3.5 times 10 to the 1, 2, 3, 4, 5, 6 inches. And you're probably telling yourself, well, that's not as good as it could be. We rounded way too much. Well, in the case of us, yes, we went through lots of different ratios, lots of different equalities. But what it really came down to is this unit out in front. This just did not show us the level of precision we needed to make such a big number. Okay, inches is much more precise than anything that we dealt with before. All right. Take a look at this last problem using dimensional analysis. And this one is the most complex one. And it's not any different than what we just did, but you'll see why it's a little more complex. So again, maybe write down what you know from here. So we have Sally Leadfoot was pulled over on her way from Duluth to Hinckley to get a donut by an officer claiming she was speeding. Okay, the speed limit is 70 miles per hour, and Sally had traveled at 97 kilometers in 102 minutes. All right, does she deserve a ticket? All right, I'm going to click over so we can see, and we'll start writing that stuff down. All right, so let's take a look at this guy. I'm going to flip this upside down. All right, so we have two different things. We know that we have 70 miles per hour. Okay, and we know that Sally was going 97 kilometers in 102 minutes. Okay, now the weird thing about this one is both of those are equalities of fractions, right? So we start with one. It honestly doesn't matter which one we start with, but because we're used to miles per hour, that's probably the unit we want to end with. So let's take our 97 kilometers per minute per 102 minutes and start there. Okay, so I took this guy because it's the only two things we know, and what we're trying to do is we're going to try to compare these units to this one, right? She's speeding if she's going over that. So this is just really a known quantity. We don't really have to use it. We could have converted that into kilometers and minutes, but then we'd have to do the math there. We might as well just figure out miles per hour, right? And so we can do that. Now the difference here is there's no one conversion for this. It doesn't matter which one of these we take care of. We got to take care of both of them. Okay, so let's take care of the kilometers first. To take care of it, I know I'm going to put kilometers on the bottom, and I can put miles on top. Okay, so when we're taking a look at that, we can go back, and I wouldn't ask you to memorize this. But if we go back to our last slide, we found out, how many miles and kilometers were equal to each other. Okay, now most of the time I give that to you, but let's just be realistic. What if I didn't know? What if I was trying to use this? One thing I do know is a 5K, right? 5 kilometers is equal to how many miles? Right? 3.1. Probably close enough. We assume that those are infinite sig figs. Now, if we really, really wanted to know, we could probably go a little bit better, a little bit more precise. But because we're using that fraction, that ratio as infinite, we're okay with that. And what we just did is we canceled the kilometers, right? And so right now, if we ended, we have miles over minutes. It doesn't matter which one's where on this. That's just what we have. And so what we need to do is the easier one is to get rid of the minutes. Now, this is where this one slightly, it's why we're doing it third, is we need to get rid of minutes. And I put it on top because it's already on the bottom here. So right now, those two would cancel each other out. Before, it's just put it there, 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 right? it comes after. But we get to some of these already ratioed numbers, and we got to deal with them in kind. And so if I want to get miles per hour, right, I can compare hours in minutes, right? And I know that for every 1 hour, there are 60 minutes. And if I take a look at what I just did, I ended up with miles per hour, which is exactly what I'm trying to compare this to. All right, so let's put in our calculator. I have 97 divided by 102 times 3.1 divided by 5 times 60 divided by 1, which we're not going to do. And I have 35.376 miles per hour, right? Taking a look at Sig Figs, remember we don't care about any of these ratios. We just care about what's in front. That's got 2, that's got 3, so our final answer can only have 2. So in this case, I count back 1, 2, that's a 3, so I round down. So I end up with 35 miles per hour is what she was going. Does she deserve a ticket? Yeah, she's slow. She does deserve a ticket. All right, so there's how you can do one of these derived equations.